preparation of alcohols. This is the where we had to deal now. How do you prepare the alcohols? So for the preparation of alcohols, we use this is the first part is from alkenes. Alkenes, these are like a double bonded systems when you have the carbon connected to the carbon and you have a double bond, and that's what the alkenes is about. And when the alkene, you have to add water to this. Addition of water means in the presence of H plus ion, that means an acid. Then what happens is, for an alkene, one side you will add OH, one side you will add H. This is how the alkene gets added, and the carbon OH group when you have, that's an alcohol. For example, you have this one. This is ethene. Ethene when treated with water and in the presence of an acid. So otherwise you can write it as H3O plus. That's also fine. That's also fine. So when you add that, you are going to get CH2, CH2H, right? CH2H, 1H here, OH here. So CH2OH. So ultimately C2H5OH. So actually these reactions are reversible in nature. So the C2H5OH is ethanol. When you see ol, that is an alcohol. And then we have to see the Markovnikov of addition. So when you have the asymmetric alkene, Markovnikov of addition means asymmetric alkene, and you have H3O plus. The negative part of the reagent, if you consider this water simply, in the water, what is the negative part of the reagent? This may not that big confusion, H plus and OH minus. So actually you should not write this when you have an acid, but still it works. This is just for remembering. You should not write this when you have an acid, but for just remembering you can write this. So you have H plus and OH minus, right? The negative part of the reagent adds to the carbon having less number of hydrogens. That's what Markovnikov's rule is. That's an asymmetric alkene. And then RCH, you have OH will be added to the carbon having less number of hydrogens, and H plus will add to the carbon with more number of hydrogens. This is just for remembering, you can do that. But you should never write this when you have an acid. Please understand, when you have an acid, the split will be like this, H3O plus, always the split will be like this, H plus and H2O. That's all the split is. Now water acid adds to this carbon. That's how you had to talk initially speaking. Okay, that's a different story. How it will add is by, yeah, you have mechanism. How it will add, you have mechanism. That mechanism, now we deal with the mechanism. That's good. You have the mechanism. Now I deal with the mechanism. How do we do that? Can I clear? Once, please note, please note.
Yes, sir.
Okay, right. Good. And now, if you have RCH double bond CH2, this mechanism is important. So here you will add H3O plus. How do you get the alcohol is the mechanism what we are going to talk. Now H3O plus, it will contain like this. So actually, this is the coordinate covalent bond. So this is how it will be, the H3O plus. And now this is a positive charge entity, and now the heavy negative charge is there because of the double bond here, electron cloud. And now this, what it does is it picks up the proton. When it picks up the proton, this bond shifts onto the water molecule. Now you see what happens. Now this is what we are adding. This is how it gets added. And now when that happens, this proton, where it can go? It has to go here or here. In principle, it will go here. Why? I will tell you. It goes to this carbon, the first carbon you can call. So R C H here at the secondary carbon, you get the positive charge, and you get CH3 here. Why secondary carbon will get positive charge? Because we know the stability of cations follows this order. This is the stability of cations. They do follow this order. Stability of the cations will follow this order. Okay, ma. Now this positive charge is coming for the secondary carbon, because this is secondary. This is a primary carbon. This is secondary carbon. This is something else. Some group is there. Don't worry about that. Now this is secondary carbon. Secondary carbon will get the positive charge. And now this positive charge, is stabilized by hyperconjugation. The positive charge is stabilized by hyperconjugation. Okay, ma. Hyperconjugation you might have learnt, but it's okay. Right now, we'll not get this into context. So to this extent, you learn. And now, because this one has left no, here the water molecule has formed. Because this proton is taken up by this. Okay. The water molecule here, it stays as it is. And now this water molecule is going to come, and this will get attached to the positive charge. Why it will get attached? Because the water molecule, it has oxygens. Oxygen is having 2 lone pairs. Because of the lone pair, there is some electron cloud. Because of that, it will get attached here. Now, after this, so you have R, C, H, O, H, H, it gets a positive charge, and again CH3 is here, right? Now you have the water molecule, this positive charge is there. Now what else can happen is that there will be another water molecule. So many water molecules will be there. Another water molecule will start picking up this proton from here, leaving the negative charge on this water, on this O. So what you get is the secondary alcohol. This is the mechanism. This is the mechanism of addition of water. This is the mechanism of, so we'll write that. What is this? Mechanism of addition of water to alkene in presence of an acid. So when you are writing an acid, remember very much, you have to remember that you should never write OH minus. OH minus will write, and remembering that here the water molecule and the proton H3O plus, that is a system. You have to work between those things only. So this is how the mechanism is. You have to give a practice in order to do this.
Okay.
Okay, ma. Now they have named the things. This is called nucleophilic attack of water molecule, and then this is called deprotonation. Like this, they have written the steps. You can verify your text. So overall, this is the reaction. You can verify and then do the steps. The first thing is the formation of the carbocation. So the initial step, this is like the formation of carbocation. So let me clear. This is the first step is formation of carbocation. So the formation of carbocation is happening. This is the first thing. For the alkene, you have the H plus will be added to the alkene. Of course, we can put a reversible arrow. And this is how you get the positive ion. And formation of the positive ion, and then followed by the nucleophilic attack of the water molecule, attack of water molecule, attack of the water molecule. That means the nucleophile. So the stepwise, if you want to write here, you have this R CH plus CH3, and the water molecule is here. It will attack here. So RCH. This is how you can write the stepwise. And then third one is that deprotonation. Deprotonation is a situation where I'll write it here itself. So I'll write it here itself. So this is the deprotonation step. So this is how you will get back your alcohol. You have to give a little bit of practice amount to get this. Okay. So minus H3O plus, you can write this. So it's a very simple mechanism, but you had to little bit, you had to give it a try. Now, after that, you have hydroboration. This is one of the most important thing. Hydroboration. This is like addition of BH3. This is like addition of, you will add BH3. You will add BH3 to the water or to the alkene. So how do you do that? This is used to prepare primary alcohols. This is very much used to prepare primary alcohols when there is an asymmetric alkene. When there is an asymmetric alkene. When there is an asymmetric alkene, this is utilized to prepare primary alcohols. Okay, what is this hydroboration? What is this addition? But they have told that it's an anti-Markovnikov's type of addition. It's not so actually. I'll explain why it is not so. It's a Markovnikov addition only. What it does is that your textbook is having some issues. Okay, ma. Now let's see this. So here, suppose you have RCH double bond CH2. Suppose you have the BH3 molecule. BH3, okay, that's called, boron what is that? B2H6 is diboron. You know this. B2H6 is diboron. From that, one piece is the BH3. And the BH3, what is the beauty of BH3 is it is a Lewis acid. Lewis acids means they have the vacant orbital. So you have, actually you won't get BH3, but you have diboron. From the diboron, we take one piece of that is BH3, and it contains the vacant orbital. It has the ability to abstract the electrons. It has the ability to take electrons. What it does, it has the ability to take the electrons. So it picks up the electrons from this double bond, and what it does is RCH, actually this is what it happens, CH2, you have something like BH3 minus will form. And now this positive charge is there. The proton, it's not the proton, H minus ion will be shifted actually. H minus will be shifted here to give you a kind of complex. So R, CH and CH2, BH2. This they have given you directly. So this step, this intermediate step, you need not remember. This one you have to remember. The BH3 will add like this, BH2 here and H here. This is the step one. Okay, ma?
Okay, sir.
Now, there's a beauty here. Now, again to this, you can add one more entity, one more alkene you can add to this. In fact, two more. As long as the hydrogens are there with the boron, two hydrogens are there, both the hydrogens can be replaced by two alkenes, three alkenes. See, BH3 is there, three alkenes can replace here. So similarly, you have B, it will be CH2, this will be CH2R. This will form thrice. In fact, it looks like this. I will draw the structure. Once you finish, I'll draw the structure. How does it look like? All the three hydrogens will be replaced by the alkyl groups actually. Three alkenes will add. Three alkene molecules will add.
Okay.
Now, how does it look like? So it looks like this. CH2, CH2R. It looks like this. Now for this, this is what the molecule is. B or CH2 thrice. So this is what the molecule is. And now when you treat this one with water and hydrogen peroxide, it's a mixture of water, H2O2 and OH minus. This mixture you have to treat this. And once you treat this, you get the primary alcohol or CH2, CH2, OH. Of course, 3 molecules are there like that. You get three molecules of this alcohol. And the other one, the other byproduct is that 3BOH thrice. This is what you get.
Okay, sir.
Okay, ma. So it always adds to the carbon. Boron, what is the thing you had remember is that boron adds to the carbon bearing more number of hydrogens. More number of hydrogens. That's the funda you have to know. Clear? Hydroporation, amma?
Yes, sir.
Yeah, the next one. Now, the third way is reduction of carbonyl compounds. So how do you reduce the reduction of the carbonyl compounds will also give alcohols. So how do you get this? RCHO is there. And then we use nickel hydrogen catalyst, or sometimes nickel palladium catalyst, or nickel or palladium catalyst, one of the things. In the presence of these, how to remember RCH2OH? Okay, how to remember this? Very easy. Very, very easy. Suppose RCHO, how does it look like? It's look like this. There's a structure. And now what they do is nickel or palladium surface, it will split the hydrogen molecule into, okay, into two atoms. Into respective atoms, it will split. And these atoms of hydrogen will add here one hydrogen here and one hydrogen here, breaking up this double bond. One pi bond. In fact, in the double bond, you have one sigma and one pi. No, the pi bond will be broken. So here, once it's broken, one part will connect to this, another part will connect to this. As simple as that. One electron. The pi bond means 2 electrons. One electron for this one hydrogen, another electron for this another hydrogen. You can simply remember like connecting like this. H, H, H. As simple. As simple as that. So that's how the reduction takes place.
Okay.
Another way of reducing is that you can take RCHO. We can use some reagent like LiAlH4. This is called lithium aluminum hydride. So this is also used for this reduction. Lithium aluminum hydride. Or you can use, if you have a ketone or something, another choice of the reducing agent is NaBH4, sodium borohydride. These are all reducing agents. LiLH4, NaBH4. These are reducing agents. Reducing agents. So these are reducing agents, NaBH4. So you have R CH2, sorry, CHOH or CHOH. The same way, the addition of hydrogen is the similar way. So 1H for this carbon, 1H for this carbon, 1H for this oxygen. 1H for this carbon, 1H for this oxygen, and remove the double bond, put a single bond. That's all you have to do. So this is how the reaction takes place. And you have one good point. Aldehydes give primary alcohols on reduction. Ketones give secondary alcohols on reduction. So this is a ketone. It gives a secondary alcohol, and this is an aldehyde. It gives a primary alcohol. Okay, am I finished?
Okay, sir.
Okay, right. Now another one. Reduction of carboxylic acids. Carboxylic acids. What are carboxylic acids? Carboxylic acids are the things which do have the COOH group. This is how the COOH group will be. This is called acid group, oic acids. And now suppose you have this one. They're taking this example. Okay. And suppose you treat this with LiLH4. These are all reducing agents, very powerful reducing agents. They will take you to this one. This I told you, this is called benzylic alcohol. Of course, if you take CH3COOH and then you treat with LiLH4, you get CH3CH2OH. Of course, this one is called benzyl alcohol. This is ethyl alcohol.
Okay, sir.
Okay, right, good. Now, so generally this lithium aluminum hydride is a very expensive reagent. So because it's a very expensive reagent, generally the industrial application is that this LiLH4, because it's expensive, they don't want to use industry. So they will use some different catalyst, a different mode. So first thing what do they do is that they take this acids, carboxylic acid, and then they treat them with an alcohol, a very cheap alcohol, in the presence of an acid. And what do you get is an ester, RCO R dash. This is called an ester. And the ester is further treated with hydrogen copper chromite. Copper chromite. Hydrogen copper chromite catalyst. So when you treat this with this one, or CH2OH, and you get R dash OH, both the alcohols you get, and then they may separate by using some distillation methods and further. So you get both from this. So for example, what do they give is like the exam, you may see this kind of question. It's like this one. Suppose this one you have, and then you have treated with H2 copper chromite catalyst, and then what you are going to get is this. It's like you break here and you make an alcohol. So here you break here and you make an alcohol here, and this portion becomes another alcohol plus C2H5OH. So 1H here, actually here this portion will take 1H here and 2H here. So like this it will take 1H there and 2H here, and then 1H for this. So that's how you can remember this, how to deal this particular reaction.
Okay, sir.
Okay, ma'am. Right. Let's move on. The next one is from the Grignard reagent. From Grignard reagents. So what are Grignard reagents? Grignard reagents are the kind of groups like RMGX. These are Grignard reagents. This delta plus and delta minus. These are the Grignard reagents. So how does this Grignard reagents will help? For example, I consider a kind of situation here. So this is HCH4. This is called formaldehyde. The formaldehyde is treated with, suppose I consider C2H5 MgBr. So this you just put like delta plus and delta minus on the carbon and delta plus on the magnesium. Now in the carbonyl, oxygen will have delta minus and then carbon will have delta plus. Add plus to minus and plus minus to plus. That's all you have to do. So I will do that here. You see what I will do. So it's like this. So CH3 CH2 minus Mg plus Br. This is how it looks like. C2H5 MgBr. And now add the plus quantities to oxygen. add the negative quantity to carbon. So how do we do that? Negative quantity, make it with carbon, plus quantity, make it with oxygen. Oxygen like this. Now, H, CH2, CH3, OH. So OMGBr, in fact, here, OMGBr, and again, H here. And then do you treat this, after forming this complex, then you treat this with an acid, you got the alcohol. So here CH3, CH2, CH3, CH2, CH2, OH plus MgBr, OH. This is how you get the reaction. So this is for the primary alcohol. So you can prepare the primary alcohol by this method. So how to prepare the secondary alcohol? Let's see that one also. So when you take the formaldehyde, you get the primary alcohols. That's the basic idea. And can I clear, ma?
Yes, sir.
Yeah. What if I take the acetaldehyde, like CH3, C, this is acetaldehyde. And acetaldehyde, when I treat this with the same CH3, CH2, MgBr, what do we do? MgBr, magnesium positive charge, CH negative charge, negative here, positive here. That's how we will act. So like a cycle, you can remember. So that's how the cycle goes. So this one is like CH3, C, O, MgBr, O, MgBr. And now you have CH2, CH3, okay, H here, CH2, CH3, H here, okay. And now we treat this with an acid, and after that what you get is MgBrOH. And now the other part is this one will become, here OH will add and here H will add. That's how one can remember. And you get CH3, CH2, CHOH, CHOH, CH3. What does this mean? This is a secondary alcohol. So what is this? It's a secondary alcohol. It's a secondary alcohol. It's a secondary alcohol. So how do we make a tertiary alcohol out of this? If you take a ketone, you take a you will make a tertiary alcohol. So this is secondary alcohol preparation by using Grignard reagents. Can I clear, Amma?
1 second, sir.
Okay, okay. Noted, noted.
Okay, sir.
Okay, ma, right. The next one. From tertiary, how do you make the tertiary alcohol? Suppose you consider CH3, C double bond O, CH3. This is acetone. And you take this CH3 MgBr. This time I'll take a very simple thing. CH3 MgBr and Mg plus and CH3 minus. Add negative to positive and then negative to positive. So like this, CH3 minus will add to the carbon, O will take the MgBr. So CH3, C, CH3, CH3, O, MgBr. And then the same reaction, and you again treat this with an acid. So here OH will add and here H will add. So you get MgBr OH and followed by, this is called tertiary butyl alcohol. So this is a tertiary alcohol. It's a tertiary alcohol for us. Clear?
Yes, sir.
Okay, ma. Only the formaldehyde yields primary alcohol. That's what you had to remember. And next is preparation of phenols. Preparation of phenols. And in the preparation of phenols, we take this benzene, and benzene is treated with oleum. Oleum, that's concentrated sulfuric acid. So you can, if you treat this with concentrated sulfuric acid, you will get SO3H group on the top of this. And then it is treated with sodium hydroxide to get sodium phenoxide, ONA, O minus Na plus, and then followed by an acid wash. You get phenol. So this is from benzene. This is from benzene sulfonic acid. Benzene sulfonic acid.
Okay,
The
sir.
next one is, okay, ma. The next one is from chlorobenzene. And from chlorobenzene, it's called Dow's process. DOWS, Dow's process. So all the named reactions are very important. What is this Dow's process? What do they do? They will take the chlorobenzene. It's actually a byproduct of the petroleum industry, something like that, as far as I know. And this Dow's process, they treat this with sodium hydroxide at a very extreme conditions, like 623 Kelvin, and the treat with this like 320 atmospheres. I think we have done this reaction in the earlier halo halo compounds, alkyl halides and haloarenes. So that is the extreme condition. They will prepare this. And 320 atmospheres, I told you, that is 320 times more pressure than the atmospheric pressure. So at these extreme conditions, you will make this. Actually, sodium phenoxide is what you get. And the sodium phenoxide is further given an acid wash to give the required phenol. This is sodium phenoxide. This is sodium phenoxide. Sodium phenoxide, you get phenol here.
Okay, sir.
Okay, ma'am. The next one is from diazonium salts. Diazonium salts. Diazonium salts we have seen in the Sandmeyer reaction. So here what do they do is they will take aniline. Aniline is treated with NaNO2 HCl between 0 to 4 degrees centigrade. So what you get is benzene diazonium chloride. So this is what you get. And benzene diazonium chloride is just treated with water and slightly warm it, you get phenol. That's phenol for you. Phenol plus N2 plus H2O. Of course, HCl. This is called benzene diazonium chloride.
Okay, sir.
Okay, next one. Next one is from cumin. This is most important reaction. From cumin. What is this cumin? So you have benzene ring. Over that you have this group. This is called cumin. This cumin is treated just with oxygen. So it undergoes oxidation. This is the industrial process actually used for preparing phenols. This one and Dow's process, both are used. And a cumin is taken and left for oxidation. This is, see, wherever there is some industrial process, those are very, very important. So this is another important thing. The oxygen just acts like this to give you this. And now this is called cumin hydroperoxide. Hydro. It's called cumin hydroperoxide. The cumin hydroperoxide is treated with an acid to get phenol. Phenol. and you get H2O2 as well as acetone as the byproducts. So this is very, very useful in the industry. Three things at a time. You have hydrogen peroxide, you have acetone, and this is our acetone, and this is hydrogen peroxide, and this one is phenol. This is how the reactions are.
Okay, sir.
Now, to see the physical properties, we will just see one physical property about the hydrogen bonding. So then we'll close. The alcohols, the physical properties wise, if you take an alcohol, so that's an alcohol you have, and now another alcohol will be bonded like this. This is how you get the hydrogen bonding. So HO, you keep maintaining H and O. So this is how you see the hydrogen bonding. Hydrogen bonding will be there in alcohols. So here this oxygen, again it will be bonded with some hydrogen. That hydrogen is connected to oxygen. That is the thing you have to remember. So OH, OH, and again here OH, like this. I hope you understood the logic how to write this. And again H is there, and again the other side it should be O. That's how it's called hydrogen bonding. Clear, Amma? So this is how you get the hydrogen bonding. Clear how to write this? They may ask this one time they asked how describe the hydrogen bonding in alcohols and showing some structure like that. Sometimes a vague question can be asked by your NCERT. So you have to be careful with this one. This is how you see the hydrogen bonding in ethyl alcohol. We have written for the ethyl alcohol. Ethyl alcohol. Okay, this is a physical property. And then for the case of phenol, how does it look like? We'll just draw that structure. That is sufficient. After that we can close this. So the phenol wise it's like this, and again O H, like this as it is. You can just follow this. So why it is like this? You see, hydrogen will get slight delta plus charge, oxygen delta minus. Connect the positives and negatives. That's all you have to do. Oxygen is more electronegative, so you get delta minus and delta plus on hydrogen. So that's the reason. So once you know the polarity, then job is done. So this is how in the case of phenols it look like. So this is what it's there in the case of phenols. Delta minus, sorry, and this is delta plus. And that's how these are hydrogen bonding in phenol. Bonding in phenols. This is how we can write, ma. So this is how one can write the hydrogen bonding structures in the case of alcohols and phenols.
Okay, sir.
Okay, ma. Let's clear today. And the next class I'll inform you. During that time, we will discuss the reactions of alcohols and phenols. So take
Okay.
care. Take care, Amma. I will inform you about the next class. Okay, ma. Bye.
Okay, sir. Thank you, sir.
Okay, ma. Bye.